We still have slightly behind in the sense that we'd like to have finished MPLS last time. So there's one more data link layer protocol we're going to look at. It's called multi-protocol label switching, right? So first of all, I'd like to give you a quick, instead of going through the historical context. So only thing I'd like to say is that, so we looked at software-defined networks. Remember that stuff? What software-defined networks are trying to do? Forgotten that stuff. So remember the data plane and the control plane stuff, and we said, you know, the control plane is normally on the routers, but with software-defined networks, we try to take the control plane, which is essentially the routing algorithms, right? That you guys distance vector link state, and then run it somewhere else, calculate the routing tables, and then send it off to the routers, right? So just to, I don't know if you recall, there was a good motivation for doing that. Do you remember any motivations for why that might be cool? Anyone? In terms of internet service providers, what do they like to do? If you're an ISP, what would you really like to do? Hard to imagine if you're an ISP, but yeah. Any ideas? What was the key thing? Yeah. Throttling, yeah, something to do with traffic. Yep. Anything good? That's right. You don't want it to be able to control your traffic flow, right? And the trouble with routing algorithms is basically they're always longest prefix match based on destination, shortest path, right? So you're limited in terms of the tools you had to be able to shape traffic and engineer traffic flow. So that was one of the motivations. So MPLS stuff predates software-defined networks, if you like, right? Okay. So, and the problem that MPLS, one of the key problems MPLS trying to address was exactly that, right? Trying to be able to provide more control over how the traffic flows were flowing across the network, right? Okay. So if you remember, this is just a rehash of a routing table. So the way that things worked in IP-based routing was that, so it did a longest prefix match. You match across all the bits, find the longest one that matched. And then eventually, so in this case, you had 1, 2, 3, 4 links, right? Doesn't matter how many IP addresses you've had, so this could be very long, right? But it doesn't matter how many addresses you had, you always map them out onto a limited number of links, right? Or if you like, the number of IP addresses was like much larger than the number of outgoing links. Typically that's the case, right? So you could have a large IP address range, but eventually the routing decision is send it down link 1, right? You had another large IP address range, the routing decision is send it down link 0, right? Okay? So, and the other thing with the way that routing worked was it was always the longest prefix match, right? And what were you matching? Source address or destination address? When you get an IP packet at a router, what does the router match in the routing table? Destination address, right? So you should know that by now. So you match the destination address and you find the one that matches best, okay? So it doesn't care where it came from, right? You don't care. You only look at where it's going, right? Okay? And then you send it out, right? So this is how IP worked. And essentially, so if you look at IP routing, path to destination is determined by destination address alone. And then what you find is that typically, although you spend a lot of time doing this matching across all these bits, the final decision is limited to sending out one of finite number of outgoing links, right? So MPLS was trying to kind of address this issue by saying, hey, you know, why do we have to make routing decisions? So in this example here, doesn't matter, this packet here comes from, these two packets here are destined for A, at this router, the routing table here would essentially go, oh, longest prefix match, send it out link 0, right? So essentially what happened was this path was always the same, doesn't matter where you came from, right? So if you were an ISP here, you're in charge of this network here, right? So if you found that this link was congested, you didn't have the ability to perhaps use this route, right? Okay? So that was a problem, right? So what MPLS tried to do was go, hey, wait a minute, so why don't we make routing decisions not only based on destination, but also based on source, right? And so when you get a packet at this router here, and this is an MPLS-enabled router, what it will do is it will look at where it came from and determine which path to take, okay? So in this example here, if it came from this source here, I would route it via R3, right? If it came from this source here, R5, I would route it via R2, right? Okay. So the cool thing here is that, unlike in the IP case, if this link was to go down, for example, right? You guys can see that. If that link was to go down, then we'd have to wait for the routing algorithms to recompute a new shortest path, right? That could take some time, okay? But in this case, you could have backup paths, right, already pre-computed. If this link was to go down, it's very easy to then route this traffic going to A via this link, right? It can happen almost immediately. Okay, you didn't have to wait for recomputing the routing tables, right? Yeah, are you following? So that's the kind of motivation behind MPLS. So how does MPLS do this? Cool stuff. Okay, very simple idea, right? Extremely simple idea. So the name is multi-protocol label switching. So MPLS doesn't really care what's after its header, right? So the idea is to have a fixed size header, right, which carries a label, right, okay, and has a bunch of other fields like TTL, like the hop count, right? And so the idea is to have insert a label between the Ethernet header, which you've seen, and the IP header, called an MPLS header, and then create a label. So this label would then essentially aggregate a whole bunch of maybe IP addresses into one, right? So you didn't have to search through multiple IP addresses, okay? So it may be a little abstract right now, but essentially the idea is to create a new header field and then insert it between the network layer, whatever is carried in that packet, and the Ethernet frame, okay? So so we briefly looked at virtual circuits maybe very, very long time ago when we talked about network layer, and we said the network layer could be using packet switching networks or virtual circuit networks. Packet switching is what internet uses. Virtual circuit is like a telephone wire connecting A to B, right? But it's called virtual because you still set up a connection via a packet switching network, right? So what that means is that you typically have established routes you always follow. So why do you need to make new routing decisions all the time for each packet, right? Okay, so it borrows some of these ideas in that saying, oh, all these labels will flow the same way, right? So you don't need to look at every IP address, for example, okay? So the idea is simple. You have an MPLS header which is basically pushed between the data link layer and the network layer address, right? And the key thing here, this is like an address, like IP address, so it's a unique identifier. And then it does have like the hop count, the TTL field, okay? So the best way to kind of look at this protocol is probably to look at an example, which is what we'll try to do next. So here is an example of, from the textbook and also in your lecture slides, is an example of a network that has a mix of IP routers, so these are IP, and then also have MPLS-enabled routers, right? So these ones talk both IP and MPLS, right? Because they're sitting between IP network and MPLS network, if you like, okay? So these are called So these routers here have a special name. They're called label edge routers. Okay. And the routers that are within the MPLS network that are running or able to look at the MPLS header and determine forwarding decisions, right, are called basically label switched routers. So like example for this one is a all right. So essentially, the MPLS routers do 3 operations. They do what's called a push. So if you're familiar with stacks, which you all are, you're computer science students. So push, like pushing something onto a stack, a pop, and a swap. Okay. So they basically do these 3 operations, right? That's all they have to do. They do a push, pop, and a swap. Push means you push an MPLS label. Pop means you take out an MPLS label. Swap means you swap an MPLS label for another label. Okay, push, pop, and swap. So they do 3 operations. So if you look at this simple network, you can see that I think this is R1, right? Okay. So you can see that here R1 has advertised to R2 and R3 that it can route to A, right? Okay, so that R2 knows that that R1 can route to A, and then R1 says that if you want me to send something to A, then send an MPLS label with a number 6, for example, in this case, right? And it says here, if you look at this routing table, it says that R1 has told R3 that I have a route to A, and if you want me to route something to A, then send an MPLS label, right, with a number 6 in it. Okay, so that's the label value. So this, trying to go through this. So what that means is that if R3 or R2 gets a packet that is going to destination A, right, it will swap the existing label, right, with the label 6 and send it down this link, right? So if R2 gets something that's headed to A, and then what it will do is it will look at, it will swap the existing MPLS label and insert one with a number 6 in it and send it down this link. So what you'll see here is that if I get an incoming label 6, right, so this is a label edge router because it's sitting, so basically your packet is leaving an MPLS network. So it will just pop this label and send it to A, right? That means remove that label, okay? So just let's go through another routing table entry. So if you look at R3 here, right, R3 has advertised to R4 here, right, that it can route to A, right, and D, okay? With incoming labels, so it can route to A and D with incoming labels 10 and 12, right? Okay. Right. So that's what that means, right? So that's how that routing table entry got there. Now I haven't told you how these routing tables were constructed because that's going to take a lot more time. But the short end of the message is that basically MPLS uses link state routing algorithm. It piggybacks on how link state routing algorithm broadcast messages, and there's a separate standard for how MPLS labels are distributed across the network, right? So that's how this happens, right? But assume for now that there is another messaging layer that takes care of distributing these label information between routers so that R3 can tell R4 that I have a route. And if you want to use my route, then you need to use label 10 and 12 to get to A and D, okay? Right? So this is a little different to the routing tables because what we have now are an incoming label and outgoing label, right? So if you look at, let's look at this routing table here. So initially you're coming in and then you're entering from an IP network to an MPLS network. So what happens here is that this label edge router will essentially, right, push an MPLS label. Let's assume that we have a packet here that is headed to destination A, all right? So when this packet arrives at R4, you'll see that unlike with IP routing, we have two choices, right? R4 has two choices. If it wants to go to A, it can either use send it via interface 0, or it can also send it via interface 1, right? So there's two established paths to get to A. So if it picks, could be based on where it came from, because could be based on traffic conditions, whatever. Let's assume that it picks to send it to R3. So in which case, what it will do is it will push an MPLS label with label 10, right? And it will send that packet here. So what goes out here will be something with MPLS label 10. So this is IP, and this is Ethernet, right? Okay. So when this arrives here, it has incoming label 10, right? And its destination is A. So what this router will do is it will essentially do a swap operation. Okay, what will it swap for? It will swap 10 for 6, right? So essentially this packet is going to have a label 6. So this is your IP packet. This is your Ethernet header. ETH. Okay. And then it will send this packet down link 1, right? So when this MPLS packet arrives at router R1, it has an incoming label of 6, and destination is A, so we'll just do a pop operation, right? Essentially remove MPLS label, and what you get now is just the IP packet and the Ethernet going to A, right? So that's pretty much how MPLS network works, right? Okay, the three operations, push, pop, and swap, right? And routing decisions are not only based on destination, but also based on source, and it's possible to have more than one route to a destination. Example here, okay? Concurrently existing in one time, right? And you can enable, disable, or change those as you like, right? Okay? So this is quite nice that in this example, if this was to go down, then I can re-enable another route, or I can insert a new label, or I can redirect traffic, for example, very quickly without waiting. So if you go to your, I'm sorry, this question was actually in last week's lecture, right? So if you go to Echo 360, but please go to last Friday's lecture, and then you'll find this question. I'll leave this on here so you guys can see it, right? Just a quick question before we move on to security. 30 minutes left. Okay. You guys can see that? Right. So have a quick think about this one. It's not too hard. So what change would you make to the MPLS table shown in the lecture to make traffic from R4 to A, right? R4 to A, so we're looking at R4 to A. Let's go these two here. This diagram's getting messy now. R4 to A. Follow R4, R2, R1. So R4, R2, R1, right? So what would you need to do? What changes do you need to make to the routing tables? Can't take too long because got some ideas? Three answers. Come on, come on. 2 minutes is too long. You guys gone lazy over 12 weeks. Jeez, come on, 3. At least 4 answers, come on. 12 weeks of studies, 4 subjects. Taking a toll, huh? At least 5 attempts. Come on, one more person. Okay, let's see some ideas. So 8A. So I'm guessing that's a mistake. So take out the first row, just send on interface 1 only. So I guess that's the idea here, is take out the first row. So first row is, I'm guessing, is this one, right? So that means we could remove this entry, right? That means there's only one path, right? And what's the other one? Push Ethernet 8 IP, swap Ethernet 6 IP, pop. So that, I guess, is the path that packet would follow. Change the first out label to 8. Okay, that's so it swap first out label to 8. Which one's that? Who said that? You mean change that one to 8? Then it would get here, it would get stuck. Because you send it down interface 0, there's nothing here, right? Any other ideas? 1 to A, 10 of interface out change. 1 to A, what is, huh?
I really typed it right, but what I meant was
Yeah.
change the first one to
This one?
yeah, the out interface to 1. No, sorry, keep that the same. Change the out interface to 1.
Oh, this one to 1, yeah. That's right. Cool. So I guess you got 3 nice answers, right? You can either remove it, or you can just edit your routing table. That doesn't matter. So if this goes 1, what would happen here, Abdul? So your label is 10. So if you get a packet here, I mean, that's a valid, but you need to make one more change, right?
Yeah.
So I get a label here with 10, but in this MPLS labelage router, there's no 10, right?
Yeah,
So you need to create it. So we need to insert another record in here, right? To say, well, if you get an incoming label of 10, outgoing 6A0, right? You'd have to do that. Yeah? No, that's okay. That's cool. So thank you. Yeah. So there's really two easy solutions to that, right? And you guys came up with both. Okay? Cool. So what do we expect? Expect you to know the motivation behind MPLS, and then how simple routing works, how routing decisions or how packets are routed in an MPLS network. Okay, like what we did today, right? The last thing I want to just mention is essentially, what MPLS uses is actually a modified link state flooding protocol to carry MPLS routing information, and there's already a signaling protocol for doing that, which is RSVPTE modification. I mean, you can look this stuff up, but I won't really ask any of that in the exam. But just remember that there is a mechanism for distributing this label information, right? And it piggybacks on how link state information is distributed across the network, okay? Probably the last important thing to recognize about MPLS is that it's nice because you can have pre-computed routes that you can enable. You can have routing decisions not only based on destination but also based on source. The other thing is also you can also have what's called virtual VPN or virtual private networks. The way to kind of think about that is if you think about a packet that has an MPLS header, it is possible to have, for example, MPLS for network 1, and then also have MPLS, let's start with N1, N2, N3, right? So you can have multiple MPLS labels, right? Labels. So essentially, in this case, this MPLS label was pushed first, and then it went to another MPLS network. Then a new MPLS label was pushed. Then it went to another MPLS network, and another MPLS network was pushed, right? So what that means is that, so when you're in network N3, all the routing decisions are based on this MPLS label, right? But when it leaves, what happens, this gets popped, just like here, when it leaves first MPLS network, right? Pop, P-O-P-P-E-D. Let's just write pop, okay? And then what you end up with is you're now in network N2 and N1, right? So it's possible to create, layers of networks within each other, right? And create virtual private networks using MPLS because it has this facility to do push multiple labels and pop, right, as you traverse through networks, okay? So it's virtual private networking support. Right. All right, let's do security. So that's pretty much the end of the data link layer. Yay! No celebratory yays, okay. I was going to bring my laptop, but I forgot. Not forgot. I ran out in a rush. But I'll bring my laptop for the next thing, and I was going to show you something, but which I'll show you next time. So reason to turn off for the last lecture. So in terms of security, basically, we don't want to go too deep. So there will be some questions at the exam on security. So I guess it's important to understand some of the tools that are available to do security and how those tools are maybe put together, right? Okay, to realize some security services, right? That's basically what we expect. So what are some of the things that forget about Trudy on there for now. So here are some of the things that are possible or in terms of possible vulnerabilities in the network. So you know that if you send something over the air, which is like Wi-Fi, then all I need is a packet sniffer, which you guys have used. It's called Wireshark. Thank you, right? So anyone just can use Wireshark, sit on the wireless network, and look at packets. And if you're typing in passwords and they're not encrypted, then, too bad. It's gone, right? Pretty much. Okay? So that's called eavesdropping, right? Anyone can just passively listen to traffic on a network, right? Eavesdrop, okay? Doesn't require any active participation. You just listen, right? And just capture stuff and look at it exactly like how you've been doing. There are plenty of tools out there to do that, okay? And then that's really bad because if you can also have active attackers where you're not only listening, but you might go, hey, here's a packet. I don't know, it's a DNS query, I'll just send a bogus DNS reply, right? Oops, just stuffed, right? And that's very easy to do because DNS requests are not encrypted, right? Anyone can read them, right? Okay, so that's an active attacker, right? Impersonation, so that means, well, you can pretend to be someone you're not. Typical problem like with spam, right? You know, if you get an email from damit@cs.adelaide.edu, you're going to believe it's from me? Who's going to believe it's from me? You're lazy or okay, you shouldn't, right? Because you don't know, really. Anyone can send an email, which I'll demonstrate in the next lecture, saying damit@cs.adelaide.edu.au, and it may not be me, right? That's a huge problem. Okay, so spoofing, impersonation, that is, pretend to be somebody you're not. It's very easy. IP addresses, they're not safe. You know, you can spoof an IP address, right? You can create a packet with whatever IP address you want and send it, right? And you might breach firewall security rules because it doesn't know. It lets through the firewall. It goes, oh, this IP address I trusted. It comes from Adelaide University. No, it's not. You just handcrafted an IP packet, right? And you might get a response back from the firewall, and you go, ha, you know something about your network now, okay? Typical example would be an IP packet that is a SYNAC. If you send an IP SYNAC, that means acknowledging a SYN, right? Then the web server will send a reset message, right? Because it'll think that it was an old SYNAC packet for a SYN packet, right? So as soon as you get the reset packet back, you know, I know an IP address or a port that's open, right? Within the firewall. Right, so you can, how do you call it? You can probe a network this way, right? Hijacking, takeover, ongoing connection. So this is typically like a man in the middle, right? So that is two people communicating, someone passively listening, and then maybe take over that connection without either party knowing, right? Okay, so we have an example of that coming later on. So this you might have heard of, right? Denial of service attacks. So this is when you have a web server you're trying to get to, you can't because it's not available. You're trying to go to your bank, ANZ or whatever, net bank, you can't get to it. It's not available, right? Because there are too many requests being sent to it and it's just gone down trying to service those requests, right? Okay, so you can create that by, think about the DNS, right? If you send a large amount of queries to the top level DNS server, you know, it'll just go down, right? Because you won't be able to keep up because there's not that many resources. And it was worse a while ago. So some operating systems, like in the 80s, even Windows only supported, I don't know, something like 8 connections, TCP connections. Maybe Linux was about 128. So if you had these kinds of servers out there, it was very easy to take them down. Right? You just send 128 requests, SYN packets, and you're down. No one else can connect anymore, right? So this stuff was really easy, creating denial of service attacks, right? Spoofing. So it's demo next lecture. So you know that it's not easy, you can't trust an IP address because anyone can spoof an IP address, right? And you can pretend to be from a network that you're not because you can handcraft an IP address. So remember that, right? Okay. Packet sniffing, which we just talked about and which you guys know about. If you send unencrypted packets that are not everyone can read, then you're potentially giving away information, right? So especially if you're on a broadcast channel, like Wi-Fi, a broadcast channel, anyone with a network card can just listen, right? Okay? And you've done some of the packet sniffing already. Denial of service attacks, which I just talked about. So, so there's the typical SYN attack that I just mentioned. Send a whole bunch of SYN packets, right? And then you have a server socket accepting connections, creating multiple, right, sockets to service the clients, but the clients are just bogus clients, right? So eventually you're going to run out of resources, okay? Well, they'll time out, but if you send large enough requests fast enough, then you can take it down, right? So it might be easy to detect denial of service attacks coming from a single host. How could you detect it? I'm an attacker, I'm just sending a bunch of SYN packets, wrote a script, right? Take down Adelaide University web server. I don't have to do exams, I don't know. Take down the web submission system. I don't have to submit my assignment. It becomes Damit's fault, right? So how would you detect that? Yeah, that's right. You can say, hey, this is unusual, right? Firewalls can detect large number of unusual requests and shut you down. So one way to overcome that is to do what's called distributed denial of DDoS, distributed denial of service attacks, right? That is, you hijack multiple clients and then get the clients to send packets, right? So you're looking at it going, oh, right, it's not from the same source, it's from actually multiple sources. So you let the packets through as a firewall, right? So this means you gotta hijack computers now out there and get those computers to run some code that sends these bogus packets, right? One way to do that would be using DNS, right? So you can send, you can create DNS request, right? And then change the source address. So, and then you might get responses from different DNS servers, right? So it may look like the replies are coming from different places, but actually to the victim whose source address you spoofed, right? So the responses go to one place, right? Okay. Oh, there's another classic one. Sorry, what about, remember IP fragmentation? So if you did IP fragmentation and you had a fragmented packet, then you send the first packet for the fragment, right? And then you send the last packet, right? And you don't send anything in the middle, right? So you have a resource that's at the end host waiting for these missing packets, potentially until a timeout, right? Forever, right? So you could do this too, right? So basically, you can exploit any part of the internet protocol stack. And there are so many weaknesses, from a DNS to DNS queries, even ARP tables, right? ARP queries, you can poison ARP queries, right? No security. You can send back ARP reply, right? Which with a MAC address that doesn't exist, right? You can poison DNS queries. You can send bogus DNS replies, which gets cached on DNS servers, right? So that when you reply, so subsequently when a DNS server uses the cached reply, it's a wrong record, right? So there's no end to the amount of security vulnerabilities on the internet, right? And every single protocol that you looked at has a vulnerability, okay? And that can be exploited, right? So how do you mitigate this stuff? Yeah. How do you mitigate sniffing, or eavesdropping, right? If you like. Okay. So idea is you scramble the packet up, you encrypt it, right? Scramble it so that the contents are only understandable to the sender and the recipient, right? Simple idea. That's what, if you're using HTTP2, comes with encryption. Or you might see, when you use your banking application, you might see that you're actually using HTTPS. So what that means is that when you guys build your web server, you used a socket, TCP IP socket, right? But with HTTPS, it uses secure socket layer socket, or SSL socket. So the way to do that is very similar to how you did it in terms of steps. A little bit more complex because you have to set up a secure socket. But what you would do is, if you wanted to change your web server to use SSL, secure socket layer, so it uses HTTPS, then you would create a SSL socket and then send the data and receive the data the same way you did, but the setup is a little bit more involved, right? So you could use HTTPS or secure socket layer, right, to create a secure connection, in which case anyone who gets those packets would know what's in it, right? That's basically how banking works, right? Otherwise, you don't want to say, I want to transfer, I don't know, $500 to Bob or whoever, and then Bob sits in the middle and goes, I'll change it to 5 million, and that's not very good, right? So you want to make sure those transmissions are encrypted, okay? So there are ways of doing that. Spoofing, how do you handle spoofing? So think about email. How would you solve spam? You could use passwords, right? Logins, would that work for email? Would using a password and login solve spam? You guys get spam? I can show you. I just cleaned my spam box because I was going to bring my laptop. But I get a lot of spam. So why can't we solve spam? Right? Because you don't know, you can't trust the sender, right? If a mail server could check on the sender, and if the sender is bogus, you could just drop it. But why can't we do that? Why is it so hard? Do you know why? Why can't we use passwords to prevent spam or prevent bogus emails from being sent? So I'm at Adelaide University. You guys have student accounts. When you log in, what do you use? Use your username and password, right? Okay, so what happens? Where are you authenticated to when you do that? Say you want to send from adelaide.edu.au an email to someone on, I don't know, gmail.com, right? So use your username and password to authenticate yourself to who? Do you authenticate yourself to Gmail or Adelaide mail server? To the Adelaide mail server, right? Gmail doesn't know. Your security credentials are at the university, right? So you've authenticated yourself to the Adelaide mail server. So now if you're going to send an email to your friend at, jane@gmail.com, so if Gmail wanted to make sure you are indeed, I don't know, let's say Damit, how would Gmail do that? So the Adelaide mail server can authenticate me using my username and password, right? But is that going to help Gmail? No, unless I also had an account with Gmail, right? And I authenticated myself to Gmail, or somehow Adelaide University shares my credentials with Gmail, right? Okay? But how many different mail servers are there in the world? Mail service providers. How many do you know? I can count like 10 very quickly, right? Yeah? Microsoft, Yahoo, Gmail, keep going. 163, right? Whatever. So many. And how many users are in the world? Potentially. You know the world population? Anyone knows the world population? Huh? What? Engineers here, you should know how to estimate. How many? 7.5 billion. That's not bad. Yeah, close to 8, right? So if everyone has an email account, what are we going to do? Everyone has a username and credential with every single mail service provider. Is that feasible? Not going to happen, right? It's not feasible. So this is a really difficult problem to solve, right? Okay, it's a difficult problem to solve, right? So username and passwords are good, but in terms of solving spam, because if we could, we would have done it by now, right? We would have gotten rid of spam ages ago. That's hard, okay? So you can't ask every user to create credentials to every mail service provider. So this is difficult to do, okay? One way to solve spoofing is to create a certificate. So that's how banking works, right? So so certificates are typically done on the server side, right? Okay. The reason that certificates are implemented on the server side is because if I go to combank.com, whatever.au, or anz.com.au, or NAB, or whatever, then I need to know that this is NAB that I'm talking to. This is Combank, right? And this is ANZ, for example, right? So the way I do that is by they issued certificate. We'll look at that in details, right? So the certificate is a way of ensuring authenticity, right? So that I know this is indeed Combank and not some attacker pretending to be Combank, right? So you could potentially use certificates for individuals, right? Why can't we get certificates, right? I can get a certificate. So you can use my certificate to say, oh, I got an email from Damit, so is it signed with his certificate? If it is, then oh, you are Damit, right? So who has a personal certificate in this class? Hands up. So there's the problem, right? Okay, so how many users do you get? 8 billion people. Everyone needs to get a certificate, right? And they're not free. Okay, you got to pay. Are you going to pay to get a certificate? Can we force everyone to get a certificate? Can we legislate around the world? It's hard, right? I don't want to pay for a certificate, right? Unless you're forced to. Maybe your company said you got to get a certificate. This is the only way you're going to, company policy. Possible. You could do that at a company level, right? So this is not easy. So if you were told to get a certificate that clearly identifies you as you, and so that is a digital certificate that digitally proves that this document came from you, like your signature, right? This is not easy to do because A, it's not free. B, you got to force everyone to have one. Otherwise, everyone can't use email, right? Okay? So none of those solutions are easy, right? So what do we do about denial of service attacks, right? We talked something, rate limiting means you can drop requests above a certain number of requests per second. Firewalls can do that. You go, hey, this web server is getting 100 hits per second. Nope, throttle, right? Okay. Limit based on IP addresses. but you know the problem with that. Distributed denial of service attacks, right? These are difficult to detect. They look like they're actually coming from different source IP addresses, right? Okay. Blacklisting, so you have known or suspected bad sources, previous history, right? So you might see sometimes when you go in the Adelaide University, if you're in Adelaide University, you try to search sites, you might say, oh, there's a security risk. We don't trust this certificate. You can't go in there anymore, right? It prevents you from getting onto certain sites, right? Because they're blacklisted sites, right? So let's stop that one there. I'm going to run out. I've got about 5 minutes. And what I want to talk about quickly is about how do we solve some of this stuff requires some kind of tools, right? And one of those tools are what's called, I feel like I've lost a slide. It's fine. So one of those tools are called symmetric key cryptography, right? Or some way of encrypting data, right? Okay. So this particular tool is pretty cool, and the way it works is that we have 2 secret keys, right? So these are all secrets. So these secrets are only known to both Bob and Alice. So I forgot to mention, in terms of security, there's multiple actors. So typically the way it goes that, Bob is in love with Alice, and Alice and Bob want to communicate with each other, and there's another third party called Trudy, who would like to break up Bob and Alice because Trudy is in love with Bob, right? Although Bob is bald and Alice is pretty nice looking, but that's the way it is, okay? So Trudy sits in the middle, and her job is to intercept these messages, change, do whatever she can to break them up. So Alice and Bob want to communicate with each other, and they don't want Trudy to find out, messages they're sending. So we said, well, to prevent Trudy from sniffing, you can encrypt the messages, right? And one tool for doing that is called symmetric key cryptography. And the way symmetric key cryptography works is that both Bob and Alice, maybe they met in one place and they exchanged, here's a key, no, don't give it to anyone, right? So they both hold these 2 secret keys, and they use the keys to encrypt messages, right? So plain text, plain text might be like, yeah, I love you, Bob, or something like that, right? Okay, and then Alice, takes her secret key and then encrypts it. So we can write it like she uses KS, right, to encrypt her message. So this creates what's called ciphertext, right? And then she sends that across. And because Bob also knows the secret key, remember these are the same, right? And that's why we call this particular kind of tool symmetric key cryptography. Symmetric means both keys are the same, right? Okay? So at some point they manage to meet and exchange keys, right? And then Bob says, okay, Bob gets a ciphertext. So remember in this case, so this is the ciphertext. Or in other words, the message that's encrypted and garbled that Trudy can't listen to. So Trudy is here. I'm sure we'll see Trudy in a minute in another slide, right? So Bob takes a ciphertext and decrypts it. So this is, if you like, decryption, which is the opposite of what happens here. This is encryption, right? So, and then recovers right. So this is one way to do that. Symmetric cryptography is used today, right? To encrypt messages. So a quick example of symmetric cryptography is substitution cipher, right? So this is really old, like, going back to, I don't know, hundreds of years. And the idea is very simple. What you do is you have a key, right? So just to go back, remember, the premise for security for these 2 guys to talk to each other is the fact that this key and this key is secret, right? If this key is revealed, no security anymore, right? Whole thing is gone. So all modern security primitives run on the same principle. That is, You don't care what the encryption algorithm is. Everybody knows the encryption algorithm. You don't want to hide it, right? If you do hide it, people figure it out